Well, we want to look at another example to expose to you all different phenomena. And again, I assume the m equal 1, b a little bigger, now it's 10. The k is still the same spring, 25. In that case, I can show you quickly this solving the initial value problem. But all you need is take a derivative, take a double derivative, put it in. I'm not going to check the equation, but I can check the initial condition. y0 equals e to the 0 plus 5 0 e to the 0, which is 1. And you take the derivative, chain rule, product rule, and you look at the 0, oh, I call it x, I call it y. And you see it's negative 5 plus 5 plus 0 equals 0. We are good. Now what you see is an exponential function, and we know this e to the negative 5t is decaying curve. It goes to 0 quickly. So if you look at the graph, that's what you have. Start from 1 in the beginning, and very quickly it dampens to almost 0. So what that mean? That means the spring is too weak to overcome the resistance. And the end result is slowly drag it back into the equilibrium point, x equals 0. So the 3 examples, actually 4 examples above, I give you all the different phenomena. The first one is a perfect harmonic oscillation, and the second one is the most typical phenomenon. It's an attenuating oscillation. The third one is just a decaying curve. So we realize that B is the only difference we discussed. So how can this B play such a role? That's our next focus. I'm going to introduce that concept first, characteristic function. First, let's look at the Euler formula you learned in the end of Calculus 2. It's e to the it, the I is the imaginary number, equals cosine t and plus sine t. That connected the trigonometric function and exponential function. So if you replace the it by negative it, then you can write this. Cosine negative t is same as cosine t. Sine negative is negative sine t. And you have the I. If you add the two, what you get is cancel out the imaginary. You got the cosine 2t, not t, times 2. You can divide the 2 to the other side. You get this trig function as the exponential function. If you subtract the 2, you're going to get this. 2i sine, the 2i I divide. So the bottom line you see from the Euler formula is I can write both the trig and exponential function into exponential function e to the rt. But the only thing is the R could be imaginary or could be a complex number. So if the R is like this IT, and then you simply remember that's trigonometric function. So the conclusion is, when we have the Euler formula, I can think all 4 examples before are a function like this. If I make the function like this, let's see. Assume your xt equals e to the rt. What's happening? Then take the derivative. It's going to be r e to the rt. Take the double derivative. You just get the r squared e to the rt. Now plug in this and this to here. I have m r squared e to the rt plus the derivative, which is br e to the rt plus k of it itself equals 0. Well, you have a common fact, e to the rt. I take it out. And then inside, I got this quadratic equation of r. Well, you know e to the rt never equals 0. Exponential function never equals 0. And then this has to be 0. So now we know where the characteristic equation comes from, and what's the connection to the second order ODE. Let me write it down here before we apply it to solve the equations. And if we start from a second order ODE like this, it's a homogeneous and constant coefficient. And then to solve that equation, we just guess the solution look like this. And the R may or may not be real. And then we end up with this quadratic algebraic equation, which is characteristic equation. Sometimes you also call it, in some book, auxiliary equation. So to look at the example here, try to solve this equation, and then all you need is identify the m equal 1, b equal 5, k equal -6. And then you get this equation r squared plus 5r minus 6 equals 0. That's the particular characteristic equation for this. We know how to solve that. We factored it out. R plus 6 and r minus 1 equals 0. Got the 2 real solutions in here. And r equal 1. That 2 real solution really give you the solution to the differential equation. Then my x1t is going to be e to the -6t. That's the first one. x2t equals e to the t. And if you want, you can call these 2 solutions as eigenvalue. That's consistent with what we are going to learn later. Once we get these 2 eigenvalues and we get the 2 solutions, so in the last step, you remember a general solution look like this. You multiply 2 constants. If I put the initial condition, the initial conditions will help you to get the two constants, and you get a unique solution. Well, that's just a quick way to see how use the characteristic equation to solve the differential equation. Since we only spent one lesson here, I'm going to shift my focus to solve the solution. You see, I used quite some time to check a solution. I'm going to let the computer do the job to solve the solution.